Hi, I'm Justin Ruths, and the core competency of my research lab is in dynamic systems and control. One of our main focuses is in the area of security of control systems, or sometimes, as we like to say, cyber-physical systems, because these are really the intersection of computing systems that are regulating a physical process. And in this lower figure, I've got a block diagram that's kind of depicting the notion that when we think about the context of attacks happening on control systems, there's a lot of really interesting questions that arise. Things get turned on their heads, and so what we do is we build in detectors that both detect attacks as well as limit what an attacker is able to accomplish without being detected. And so the basic idea of the tools is the fact that we leverage knowledge about our system. So in particular, what a system's allowed to do and what it's not allowed to do based on its dynamics, its process dynamics. And we use a model of those dynamics to predict what's going to happen. And when that model deviates from what we're measuring, we essentially get concerned and we establish thresholds where if that deviation between what we predict and what we receive from sensors gets too large, then we can raise some sort of alert or an alarm. The sensitivity of that is really regulated by how much we know about the system. And so things like uncertainties and noises play really important roles in our ability to limit what the attacker is able to accomplish. And so the big picture of what we're doing is devising new detectors, analyzing them to understand their sensitivities and how they relate to different types of uncertainties that happen in the system. We're interested in quantifying and designing attacks on systems and then figuring out what kind of impact those can have on the actual system once those attacks are initiated. And so that brings to bear a lot of different tools that we have in control theory, things like reachable sets, like stochastic systems, and all sorts of other things. Another big theme in our research is on networks, and so there we're really interested again on the control side and understanding how we might leverage structure, because that's really what networks encode, structure of a system, to understand how we might control that. And here we're thinking about really large scale systems, things like populations, really big systems that require us to look at them at this kind of higher network level rather than our typical differential equation perspective. And so here there's essentially establishing connectivity or connections between the network structure and some of these properties. So that's a bit of a balance between network science, graph theory, and control theory. Along the way, a really interesting question, an important question, is being able to infer structure and dynamics from data. And so one of our really interesting application areas is in the area of the brain. And so you can model the brain at a ton of different levels. But the idea here is that whether you're modeling it at the neuron level or brain region level, there's kind of two questions when you want to start interacting with that system. And so one of them is what we call the inference problem. So what is the structure? And one is what is the network problem? So where in that network to apply a stimulus or to affect a change in that brain behavior. And then on top of that, we've got the control problem, which is assuming that you've got the structure and got the network and know where you want to place your location of controls. What kind of stimulus are you actually driving? So what is the electrical voltage that you're gonna apply at these points in the network? So it's a concrete example. In terms of security, we have two test beds, and this is down in the lower corners. With these QR codes. One of them is a process control system, and so that gives people access to real industrial control system, computing systems and all the right infrastructure and hardware that go along with that. And then we also have this what's best called a golf cart, but it's almost a car, where we are slowly making that autonomous, and this is where we get a lot of undergrads involved in our research. Getting that to be autonomous and then starting to look at some of the challenges, thinking about that as a control system and thinking about the security challenges there. So a lot of opportunities in networks and in security of control systems.